Hi, and welcome back to Keys Precalculus. This is the last half of section 5.5. We are going to look at the product to sum formulas and the sum to product formulas for trigonometric functions. The product to sum formulas can be verified using the sum and difference formulas from the previous section, and then the sum to product formulas are the reverse of the product to sum, and those can be verified, or those are proven in the Appendix C section of your book, if you'd like to look at it. We are going to use these formulas to write products and sums. We're going to use it to to verify trigonometric identities. We can use them to solve trigonometric equations, and we can use them to find what the sine or the cosine of a particular angle is. The product to sum formulas, they are often used to evaluate integrals in calculus, the integrals involving products of sines and cosines of two different angles. So they are useful, and you do need to become familiar with them. These formulas can be found on pages 379 and 380 in your book. Let's look at example 8 on page 380 in your book. Right now it says to rewrite the product that they give you as a sum or a difference. So we can see that the product they gave us is the cosine of 5x times the sine of 4x, or the cosine of u times the sine of v, which matches this particular formula right here. So we are going to rewrite cosine 5x sine 4x as half of sine of u plus v minus sine of u minus v. So let's figure out what our u's and our v's are. Our u is 5x, so I'm going to underline all the u's here in red. Whoops. And right there. And our v is 4x, which I'm going to underline all my v's in green. So I'm going to rewrite this as 1/2 times sine of 5x plus 4x minus the sine of 5x minus 4x. And then when I simplify this, I get 1/2 times the sine of 5x plus 4x, because they're like terms I can add them, becomes 9x, minus the sine of 5x minus 4x, because they are like terms I can subtract them just to get x. And so it becomes 1/2 sine of 9x minus 1/2 sine x. And that's all I have to do. I was just rewriting my this product as a difference. Just showing you, and this was just an example to show you how to convert between the two. Example 9 on page 380 shows us how to use the sum to product formula to find the exact values of the cosine or sine of different angles. Now here we've got cosine of 195 degrees plus a cosine of 105 degrees, and they ask us to find the exact value. These are not like terms, so I can't just add them and say find the cosine of 300 degrees. It doesn't work that way, because the cosine of one angle is not the same as the cosine of another angle, not necessarily the same. So I'm going to look at my sum to product formulas, and I find that the cosine of 195 plus the cosine of 105 is this product right here, which can be rewritten as 2 times the cosine of u plus v over 2 times the cosine of u minus v over 2. So I'm going to go ahead and rewrite that using my u's and my v's. U being 195 and v being 105. I'm not going to change colors in this one. So I get 2 times the cosine of u, which is 195, plus v, which is 105, and that total divided by 2, times the cosine of u, again, which is 195, minus v, which is 105, divided by 2. Okay, when I simplify, I'm going to get 2 times the cosine of 195 plus 105 is 300 divided by 2 is 150, so the cosine of 150 degrees times the cosine 195 minus 105 is 90, and 90 divided by 2 is 45. And we can find quickly and easily on our unit circles the cosine of 150 and the cosine of 45 degrees. So the cosine of 150 is negative square root of 3 over 2, and the cosine of 45 is the square root of 2 over 2. So when I multiply this out, simplify it, I'm going to get 2 times negative square root of 3 times square root of 2, so that's going to give me 2, or it says negative 2, times the square root of 6 over 4. And when I reduce that, or simplify it, I get negative square root of 6 over 2. So the product, the sum of the cosine of 195 degrees plus the cosine of 105 degrees is negative square root of 6 over 2. Okay, now we're going to use these special formulas to solve for x, to solve a trigonometric equation. Okay, so if we look on example 10 on page 381, it says to find the solution to sine of 5x plus sine of 3x equals 0, or rather find all the solutions in the interval from 0 to 2 pi. The sine of 5x and the sine of 3x are not like terms. I can't just add them. But because they are sums of trig functions, I can look to my sum to product formula and see if I can rewrite them as a product, and that might help me solve this. So if I look up here in my sum to product formulas, I see that it is equivalent to sine u plus sine v, u being 5x and v being 3x. So I'm going to rewrite them as 2 sine of u plus v over 2 times a cosine of u minus v over 2, and see if I can simplify it that way. So as you can see, I rewrote sine of 5x plus the sine of 3x as 2 sine of 5x plus 3x over 2 times the cosine of 5x minus 3x over 2. And now I do have like terms I can use to simplify this. So this becomes 2 times the sine of 5x plus 3x is 8x divided by 2 becomes 4x. And the cosine of 5x minus 3x is 2x divided by 2 is just x. And that is equal to 0. Now I have 3 factors, 2, sine of 4x, and sine 4x and cosine x. If I divide everything out by 2, I get sine 4x cosine x equals 0. Now I have 2 factors that I can set equal to 0. I can say sine 4x equals 0 and cosine of x equals 0. So now I'm going to come up here and I'm going to simplify this. Sine of 4x equals 0. Now I shouldn't just say what angle gives me sine of 0, gives me a sine of 0, and then say 4x equals whatever that is, and then solve, because that doesn't give me all of the solutions. It only gives me 2 of them. And there are actually 8 solutions to this in the interval from 0 to 2 pi. So because I'm taking the sine of a quadruple angle, I'm going to use my double angle formula to simplify this, and then I'm going to use it again. So I can rewrite this as the sine of 2 times 2x. So this is like I'm using the multiple angle sine of 2u. So if I look back at my double angle formulas on page 375, I know that the sine of 2u is equivalent to 2 sine u cosine u. Therefore, since my 2x is my u, this is the same thing as saying 2 times the sine of 2x cosine of 2x. And then I can use my double angle formula again, or actually before I do that, I've got to set all of these equal to 0. And if I divide everything out by 2, then that 2 goes away, because 0 divided by 2 is 2. So it can now be rewritten as the sine of 2x times the cosine of 2x equals 0. Now I can simplify the sine of 2x again, and I'm going to, it becomes 2 sine x cosine x, and I'm going to leave cosine of 2x the way it is. There's a reason for that. I'm going to go in circles if I don't. So then if I divide out by 2 again, then I get sine x cosine x times cosine of 2x equals 0. And I can set each one of these equal to 0. So because they are each factors. So sine x equals 0, cosine of x equals 0, and then the cosine of 2x equals 0. Now here, when the sine of x equals 0, that happens, or sine is 0 when x is equal to 0, or it's equal to pi in this interval. And the cosine is 0 when x is equal to pi over 2, or 3 pi over 2 in this interval. And then the cosine of 2x, cosine is 0, again, when 2x equals pi over 2, or 2x equals 3 pi over 2. But when I divide both of those sides by 2, then I'm going to get x equals pi over 4, and x equals 3 pi over 4. But I'm also dividing my period in half. So this is going to occur again at pi units later. Pi units later. So pi over 4 plus pi is going to give me 5 pi over 4. And 3 pi over 4 plus pi is going to give me 7 pi over 4. And I'm running out of room. I'll squeeze it in here. 7 pi over 4. So we have 8 answers. X is equal to 0 pi, pi over 2, 3 pi over 2, pi over 4, 5 pi over 4, 3 pi over 4, and 7 pi over 4. That's not in order. But if I were to go back over here to my original, over here it's at cosine x equals 0, I'm still going to get the same answers of pi over 2 and 3 pi over 2. They're just repeats. So that's not all in the example in your book. I broke it down a little further. They just gave you the answers. But that is how you would solve something like example 4. I didn't say 4, example 10. Your homework is not going to be that complicated, I don't think. Now let's do one more example. We're going to do the last example, 11, where we're going to verify a trigonometric identity using our sum to product formulas. Okay, example 11 on page 381 asks us to verify this identity of sine t plus sine of 3t over cosine t plus cosine of 3t. They want us to verify that it equals tangent of 2t. So we're going to use that using the sum to product formulas. And we've got to use a couple of them here. We've got a sine u plus sine v over cosine u plus cosine v. So we are going to be using this sum to product formula and this sum to product formula. My u is t and my v is 3t, and I'm going to work with just the left side. I'm going to use the first formula to rewrite the numerator. So I'm going to rewrite the numerator as 2 times sine of parentheses the u, which is t, plus the v, which is 3t, divided by 2, And I meant to make my parentheses all the way down. So let me correct that here. Plus, not plus, times cosine of t minus 3t divided by 2. That's my numerator. My denominator, I'm going to use the third formula. So it's going to become 2 times the cosine of t plus 3t over over 2, times the cosine again of t minus 3t over 2. And I'm going to go ahead and put it equal to tangent of 2t. Now I'm going to simplify this down. Since these are factors, I can cancel out the 2's, right? And then the sine of t plus 3t divided by 2 on the numerator is the same thing as saying the sine of t plus 3t is 4t divided by 2 is 2t. And also on the numerator, the cosine of t minus 3t divided by 2 is negative 2t divided by 2, which gives me the cosine of negative t. There should be a negative there. That should be my numerator. Now my denominator simplifies to cosine, doing the same math of 2t times the cosine, the same math, of negative t. And that should all be equivalent to tangent of 2t. Because I have common factors in my numerator and denominator of cosine of negative 2t, I can cancel those out. And I'm left with sine of 2t divided by the cosine of 2t. And sine over cosine is equivalent to tangent over 2t, so I have verified this identity. I think that we've done enough examples for you to do your homework, and then I will answer any questions that you have when we come back to class on Tuesday. Y'all enjoy your weekend.